Sure. What's up? I don't think the microphone here is working. Um, Struggle with your sheet. Yeah, of course, of course. Yeah, so if you can't make it to my office hours, I mean, you can always just email me the question too. I think most people, if you have a question on a specific problem, you can always just email me. And if it warrants kind of further discussion, I can just say we can be in office hours. But most of the time, I try to answer everyone through email. Just because I know it's kind of hard to come to office hours if it's in the middle of the day. So, yeah, go ahead and email it to me, and then if things aren't clear or if um, okay, yeah, that's no problem. I think the microphone here at the or the speakers in the classroom don't really work anyway. So even if you were speaking, then I don't think I could hear you. But yeah, go ahead and email to me, and then I'll try my best to kind of help you through email. But of course, you're definitely always welcome to come to office hours too. It's just I know office hours in the middle of the day. It's kind of hard for grad students to make it. So yeah, I'll try to help you with email first, and also just because I don't have office hours tomorrow. My next office hours will be on Thursday, so I probably if you email me tonight, I can probably get to you tomorrow morning. Yeah. Oh yeah, it's yeah. These homeworks are just kind of rough in general, and so all the direct stiffness problems are um not fun. I think just to kind of put it lightly, just because it's a lot of calculations, it's a lot of matrices. So yeah, it is tough. Yeah, I would definitely say remember that all the lecture recordings are posted on YouTube. The links for that are on the Canvas site. So yeah, definitely check those out when you're feeling better. First exam, let me check the date on that. I don't remember exactly. Usually it's a week 7. That's when I usually like to have my exams. Um, but for this class, I might have pushed it back. So first exam is going to be all direct stiffness stuff. And so um, basically it's going to be everything we've covered so far. It's going to be what we're going to cover this week in beam equations. And then we're going to cover one more topic after this called frames. So that's kind of what I had planned for the first midterm. So date for the first midterm, it is planned for Tuesday, March 10th. So about a month from now. Yeah. Mhm. All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing? Good. Everyone have a good weekend? Good. Yeah, it suddenly got cold today. It was actually quite nice over the weekend, and then all of a sudden it's cold. Um, okay, question for the chat. So would you say homework and review would be good enough for? Yeah, so I definitely write the homework problems. So I mean, I write my own homework problems. I'm also writing the exam problems, and so they're very much going to be in the same style. We'll talk a bit more about kind of the explicit format for the midterm exam once we get a little bit closer. But yeah, the homeworks are great practice. I'm going to post a study guide when we're closer to the exam as well. I would definitely look at those two to start. One thing you'll also have for the exam is that I also let students bring just a sheet of notes. And so that's an 8.5 by 11 sheet. You can use both sides. So definitely make good use of that too. So one thing we'll discuss later on is that, I think people just like to just, copy things onto their cheat sheet last minute. But if you actually really kind of take the time and kind of, distill the information down into a cheat sheet, you'll see that that's already a great studying tool already too. So, but yeah, we'll discuss kind of more once we get closer. Okay, all right. So the plan for today is we're going to be going over beam equations, and so we're going over a new element type today. It's actually quite a bit different from our springs and trusses, and so that'll be kind of a big change. And then we're just going to work on some examples from there. So from here on out, the class is or the next couple of weeks are going to be pretty structured. So for the next couple of weeks, we'll introduce a new element type at the beginning of the week. We'll do some problems with it. And then, we'll move on from there. And by the end of next week, we'll actually start to bring MATLAB into play. And so, this week and next week, I think will be, I think a kind of a transition from in that sense. But this week is just focused on beams. And so we'll kind of get that out of the way this week and then move on to other stuff next week. Okay. All right. Any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. Okay, so let's talk about beam equations. Okay, so far, we've introduced this idea of the direct stiffness method as a way to solve for the finite element solution to, certain problems that have have elements of a certain type, right? And those types of elements that we've gone over so far are springs and trusses. Okay. It's kind of almost, not really legitimate to call springs and trusses different elements because they're essentially the same. The only difference is kind of the coefficient out in front, right? But springs and trusses share the exact same behavior in the fact that, we only consider axial deformation for these types of elements, right? So you can draw a truss, you can draw a spring, right? Essentially, they're the same. We're only considering, forces and deformations that go down the length of the element. So we call this axial deformation. All right, so I think other ways that we've described this is that springs and trusses can only support tension and compression, right? So basically any forces that are along the long axis of the element. Okay. Now, this is not the only way that structural elements can deform, right? And so, we have situations where we have, deformation that is perpendicular to the element, right? And so that's how we kind of introduce beams. Okay. Right. So this will be kind of the first time that we're looking at situations where our deformation is not going in that particular direction. Okay. And so beams in particular support two types of degrees of freedom. Okay. And so the first type is what we call transverse deformation. Okay. And the other type is rotations. All right, so schematically it looks like this. And so we have an element here, it's a beam. Okay. Usually for beams, I'll draw it as a rectangle. And so, I won't kind of draw the little circle for the cross section. So that's kind of a very subtle thing, just personally what I do, but that's not a standard convention. That's just my own personal thing. Okay. So transverse deformations are deformations that are perpendicular to the length of the element. Okay. And so transverse deformations, we have basically U, or I should say D. Okay. Right. So we'll have D1Y, which is the deformation, upwards on this element, and then D2Y. Okay. So that's going to be the transverse deformation on the other side of the element. Okay. And then the other thing we'll have is rotations. And so we'll have a rotation is basically just a change in orientation, right? Okay. And so theta 1, theta 2, those will be the rotation angles for our element, at the two nodes. Okay. Okay. So with two types of degrees of freedom, two nodes per element, a beam is always going to have at least 4 degrees of freedom associated with it. Okay. Now I say at least 4 because this is for the plane case where our element is completely flat. But if you were to look at 2D beam problems where our beam is kind of all angled up, with respect to the horizontal, you're going to have to cover both Cartesian deformation directions. So D1x, D1y, D2x, D2y, just like we did with the trusses. Okay. But if you're looking at a perfectly flat beam, where the transverse deformations align with the y-axis. So that's kind of the standard position. Then we have 4 degrees of freedom. Okay. Okay. So first step that we need to do, just like we saw with trusses and springs, that we do need the element stiffness matrix for beams. Okay. So we can go through and we can derive the element stiffness matrix for a beam element, just like we did previously. Okay. That was kind of what I had planned to do last Thursday, except we had the fire drill that kind of prevented that, and so I'll just kind of put the highlights for the derivation here, but just know that all the detail is in the lecture notes. Okay. Okay. So the derivation follows just as just kind of a natural consequence of beam theory. So we start with basically just an equation that describes the transverse deformation of a beam. Okay. So that's E times I multiplied by d4 dy over dx to the fourth power. Okay. Right, so that's kind of our beam equation there. You know, we did apply some assumptions here. So we basically assumed that the E and the I are constants, and we also assume that there's no distributed loading, so there's no body force term. Okay. So essentially what you do in the derivation is that you take this equation, you apply it to the beam, you set it equal to the nodal forces at each end, and from there you're able to get four linear equations. Okay. Okay. And those four linear equations form the four rows and columns of our element stiffness matrix. Okay. Okay. So again, you know, the details for this derivation are in the notes if you are interested, but I'm just going to go ahead and skip to the end just so that we can kind of start doing problems. Okay. Okay. So the end result is the following. So what you're going to, first thing you're going to notice is that this element stiffness matrix is quite a bit more complicated than the element stiffness matrices we've done so far. And so these ones you kind of have to be really careful when you're plugging in values. Okay. Okay. All right. So first, let me write out the matrix first, and then we'll define all of the terms. Okay. All right. So first thing we have is we have this coefficient out in front, which is E times I divided by L cubed. Okay. And then to this, we're going to multiply by a 4x4 element stiffness matrix, right? Since we have four degrees of freedom. Okay. All right, unfortunately, this is not, there's no easy way to do this. And so let's just kind of write it out. So we have 12, 6L minus 12, 6L. All right, so but one thing that is consistent here is that our element stiffness matrix is symmetric. And so just like we did with our 2D trusses, whenever you write a row, you can write those same values into the column as well. Okay, so we know our first column here is going to be 6L minus 12, 6L. Okay. Next, we have 4L squared minus 6L, 2L squared, okay, minus 6L, 2L squared. Okay. Then last two rows, we have 12 minus 6L minus 6L. Okay. All right, question. So do you need to know how to derive the equations for beam theory on the homework? So there is a conceptual question about that, just in terms of you know, how do you kind of derive this? So I would definitely look at that in the notes to kind of see. But the question is fairly straightforward. Yeah, you should know, you know, at least conceptually, you know, what some of the details of that derivation. Yeah. But that's not on. That's the, well, actually, yeah. So that is on the current homework. So homework 2, there should be a conceptual question. I think it's the last one. Yeah. Mm-hmm. Okay, and then our degrees of freedom here, this is going to be dy1, theta 1, dy2, theta 2. And this is equal to f y1, m1, f y2, m2. So this is our element stiffness matrix for a beam. Okay, so let's go ahead and define these constants here, just because there's quite a bunch of new variables that we haven't seen before. A lot of them that we have seen, but some that we haven't seen before. Okay. Okay, so E has the same definition as our truss element. So E represents the Young's modulus for this beam. So Young's modulus is a property of the material. And so that basically tells you how strong that material is at resisting just general deformation. So the higher the Young's modulus, the stiffer the material is. Okay. L, this also has the same definition from our truss element. So L is just the length of the element. Okay. Next, we have I. So I is a new one. So I here is the moment of inertia of the beam's cross section. All right, so that's all the material and geometric properties. Let's define everything in the solution vector and the forcing vector. Okay, so d1y, d2y, these here are the transverse deformations of our two nodes, node 1 and node 2. Next, we have theta 1, theta 2. Okay. So theta 1, theta 2, this represents the rotations of the of our two end nodes. Okay. Right, and then our forcing vector, let's define those. So F y1, F y2. These are the transverse forces that are being applied on the nodes. So these are forces that are applied in the direction perpendicular to the element. Okay. And then M1, M2, these are moments that are applied on the two nodes. So moments could be something like a torque or something kind of a, something that's going to cause rotation. Okay. Okay, so a lot of variables, and I know this matrix here. Well, once you kind of use it a few times, you start to kind of see it in your dreams. But before that, it's a lot to kind of memorize here. So definitely have this handy. And then yeah, any questions on this so far? Okay. All right. So before we jump into an example, let's talk a little bit more about constraints. Because now that we've kind of introduced this idea of a rotational constraint or a rotational degree of freedom, there are certain constraints that will restrict that and certain constraints that will not. Okay. Okay. All right. So in general, so far there are three possible degrees of freedom that can occur at any given node. Okay. So the first one that we've been using up until this point is axial deformation. Which, usually, for a coordinate system that's local to the element is in the x direction. Okay. So dx. Okay. I guess technically that's dx hat. Okay. Next, we have transverse deformation. Okay. So that's dy hat. Okay. So that's the new one. That's the one that we've just learned. Okay. And then 3 is, of course, rotations. So interestingly, rotations are kind of independent of the coordinate system. And so, it doesn't, because rotations are unitless. And so it's not something that depends on the coordinate systems or any degree of measurement. Okay? So rotations are just going to be theta. Okay. Now, we can apply different types of constraints to restrain these degrees of freedom. Okay. And so in general, there are three types of constraints that we can use. Okay. Okay. So the first type of constraint that we have is what's called a fixed support. Okay. So a fixed support is the strongest type of constraint that you can have. In a fixed support, all of our degrees of freedom are going to be constrained. Okay. So usually, schematically, it looks something like this. Okay. So usually, you're going to have some wall. You're going to have a beam coming out of it. Okay. And so the fact that this beam is basically attached to this wall, that is our fixed support. Okay. And so again, under a fixed support, dx hat, our axial deformation is going to be 0. Our transverse deformation is going to be 0. And theta, our rotation, is also going to be 0. Okay, so fixed support constrains all 3 degrees of freedom. Okay. All right, so next one we have is a pin support. Okay, so this is one that we've mostly been using just because we haven't considered rotations up until this point. Okay. So for a pin support, it usually looks something like this. And so you have an element and basically a little kind of pin there that's pinning it, and then the pin itself is fixed to the ground. Okay. Now under a pin support, both of the deformation components will be 0. So dx hat's going to be equal to 0, dy hat's going to be equal to 0. Okay. But our rotation is going to be free, right? And so because it's a pin, what we're saying is that the element there, even though it can't translate, it can't move from that spot, it can at least change orientation. It can change direction. Okay. And so that means our theta is going to be free. Okay. Okay. And then finally, we have a roller support. Okay. So this is one we just introduced just last time. So under a roller support, we have basically a pin that's attached to the element that's on wheels. Okay. And the roller support only constrains deformation that's perpendicular to the ground. Okay. So in this case, if we say that the x direction, again, is along the length of the element, that means dx hat. There's no restrictions on this just because it can roll in that direction. So we say dx hat is free. dy hat is 0. So the transverse deformation is constrained because of the roller. And then our rotation is free as well, okay? Because the roller is kind of just like a twist on the pin support. And so the element is free to kind of rotate and change angle at the roller support, okay? All right, so starting with these beam problems, you'll see a combination of these types of constraints in your problems. And so, when you go to apply the boundary conditions to your global linear system, you want to make sure that you don't accidentally knock out a row that's not supposed to be knocked out. Okay, so definitely be aware of the type of constraints that you're using and what effect that has on your matrix. Okay. All right, any questions on this? All right, so besides that, that's all the new information about beams. And so, we have our new element stiffness matrix, we have these new constraints. From here, solving these FEA problems with beams is the exact same process as before. The only difference is that, we have a different element stiffness matrix. Okay. All right, so let's do a quick example. Okay, so let's look at the following configuration. So we have a wall here. You have an element that's fixed to it. Okay. Okay. And then this beam kind of keeps going. Okay, so we have a 2-element system. So we have an element A on the left, element B on the right. It's not supposed to be angled. I'm just really sleepy because I only got 2 hours of sleep last night. It's supposed to be straight. So just kind of imagine. Well, let me redraw. I'll redraw it just straight. Okay. No excuses. We gotta draw it correctly. All right, there we go. More straight than before. Okay, so you have two beams, beam A, beam B. They are completely flat. Okay. They both have the same length. We have a pin support on the right-hand side. Let me label the node. So the node attached to the wall, this can be node 1. This one here is node 2. At the end here, we have node 3. Okay. And we have two loads that are being applied onto this beam here. Okay. So at the midpoint, we have a vertical force. So we'll call that P. Okay. And then we also have a torque that's being applied as well. So also at node 2, we're going to assume that we have a counterclockwise torque, which we're going to call M. Okay. Okay. So for this problem, we're basically going to do this problem all with symbols. So I'm not going to give you any numbers, just so that we can kind of see the process. But we're going to assume that E and I are known. Okay. And we're also going to assume that both elements have the same Young's modulus and the same moment of inertia of their cross section. Okay. Okay. And so knowing the fact that elements A and B here are beams, okay. All right, so all we can do in this problem, just because we don't have any numbers, is we can set up the global linear system. All right, so fairly standard finite element problem. We're not given any numbers, and so we're just going to do the whole thing with symbols. We're going to go fairly quickly, and then we'll go. Okay. Any questions just on the setup of the problem? Okay. All right, so let's go ahead and get started. So, just like any finite element problem, we are going to start with the element stiffness matrices. All right, so luckily elements A and B are exactly the same, or at least they have the same properties, the same length, the same Young's modulus, the same I. Okay. And so numerically, the two element stiffness matrices will be the same. But remember, each element stiffness matrix is connected to different nodes. And so we want to make sure we note that as well. Okay. All right, so let's look at node element A, excuse me. Okay. So we have just a generic beam. It's oriented in the right way. We know all the properties. And so let's just go ahead and write out the element stiffness matrix. Okay. So that's going to be E times I divided by L cubed. Okay. Multiplied by 12, 6L minus 12, 6L. Okay. And then 6L minus 12, 6L. Okay. And then 4L squared minus 6L, 2L squared. Okay. And then 12 minus 6L minus 6L, 4L squared. Okay. Okay, and then element A we know is connected to nodes 1 and 2, and so we're going to factor that into our solution vector here. This is d1y, theta 1, d2y, theta 2. Okay. All right. So it's a little anticlimactic just because we don't have any numbers to plug in, but In some ways, this is kind of good for our first problem, just to kind of see. Okay. Okay, so let's do the same thing for element B. So element B will have the exact same matrix. The only difference is that element B is connected to nodes 2 and 3 as opposed to 1 and 2. Okay. All right, so I'm just going to write this one fairly quickly. So we have 12, 6L minus 12, 6L, 6L, 4L squared, or excuse me, 6L minus 12, 6L, 4L squared minus 6L, 2L squared minus 6L, 2L squared. Okay. 12 minus 6L minus 6L, 4L squared. Okay. And then element B we know is connected to nodes 2 and 3. So let's go ahead and make note of that as well. So it's going to be D2Y, theta 2, D3Y, theta 3. Okay. All right, so fairly straightforward. So all we've done basically just taken our formula for the element stiffness matrix and just kind of moved it down here. Okay, just because we don't have any numbers just yet. Our next example will have numbers, but for now we're just doing one without the numbers. Okay. All right. Any questions on this so far? Okay. All right. So now that we have our element stiffness matrices, we are ready to assemble. So let's go ahead and do that. So for assembly, we have EI over L cubed. Okay. Since both elements are the same, I'm just going to factor out that same quantity just so we don't have to worry about it. Okay. Our global linear system here will be 6 by 6. And so let me go ahead and write the columns in. So we have D1Y, theta 1, D2Y, theta 2, D3Y, theta 3. And then rows, we have D1Y, theta 1, D2Y, theta 2, D3Y, theta 3. And then out here we have F1Y, M1, F2Y, M2, F3Y, M3. All right. So now that we have our global linear system set up, we can go ahead and start plugging in our element stiffness matrices. Luckily, our element stiffness matrices here are pretty straightforward. So they all are just using consecutive nodes here. And so element A will be nodes 1 and 2. Okay. So element A is going to be this region right here. Okay. That's element A. So element A is nodes 1 and 2. And then element B we know is nodes 2 and 3. Okay. And so let's go ahead and block those off. That'll be that region right there. Okay. Okay. All right, first thing we'll do is, any regions that do not have a box around them, we'll go ahead and put zeros there. Okay. So we're going to have zeros basically at, in the rows and columns where nodes 1 and 3 interact, right? So that's the D1Y, D3Y row, D1Y, theta 3 row, right? And that makes sense just because there's no element that's connecting nodes 1 and 3. And so there's no way for those two nodes to interact, right? And so it makes sense that we have 0 there. Okay. Okay, so let's go ahead and write in the entries of the matrix now. Okay, so let's start with element A. So we have 12, 6L, minus 12, 6L, 6L, minus 12, 6L, 4L squared, minus 6L, 2L squared. Okay. All right, in the overlap part, we're going to leave some extra room just because we know we're going to add the entries from element B that overlap with that one. Okay, so we have a 12, minus 6L, minus 6L, and then 4L squared. Okay. Okay, so let's do the same thing for element B. So element B is the exact same matrix. It's just, how we put it in is different. Okay. Okay. We're going to add a plus 12 here, plus 6L, okay. Minus 12, 6L, okay. Plus 6L, minus 12, 6L. Okay. Second row, we have a plus 4L squared on the diagonal entry. Then we have minus 6L, 2L squared. Then the bottom right, we have a 12, minus 6L, minus 6L, and then 4L squared in the bottom rightmost entry. Okay. These problems never get any easier. It's just a lot of tedious kind of writing here. Okay. All right, so in our overlap region, let's go ahead and perform that arithmetic. And so in two cases, you see that we have an increase in the magnitude of the entries there. So those are our two diagonal terms. And so we have a 12 plus 12, which is going to be equal to 24. Okay. And then in the bottom right, we have a 4L squared plus 4L squared. That's going to combine to 8L squared. All right, and then in the off diagonal entries, we have minus 6L plus 6L in both of those. And so that's going to cancel out and give us zeros on that. Okay, all right, so that is our assembly. Okay. Same process that we've gone over, just just with different element types now. Any questions on how we've assembled this matrix here? Okay, and so last step that we have here is we're going to apply the boundary conditions. Okay, so this part is kind of the new part, and that's kind of the whole reason we're kind of going through this whole example. Okay, so let's go back up to our problem and let's make note of the types of boundary conditions that we have on our two nodes, right? Okay, so if we look at the constraints first, right? We see that node 1 is fixed to the wall. And remember what a fixed support means. A fixed support essentially means that all degrees of freedom at that node are going to be knocked out. Okay. So that means that node 1, d1y is equal to 0, theta 1 is equal to 0. Okay. And then on the rightmost node, we have a pin support. Okay. So that means d3y is equal to 0. Okay. But since it's a pin, then we know that the rotation at node 3 is going to be free. Okay, so we're not going to constrain theta 3. We're only going to constrain d3y. Okay. Okay, so let's go back to our matrix. Let's go ahead and see that happen. So first we're going to do is we're going to apply the fixed support on node 1. Okay. So that's going to knock out both of these rows here, the first two rows. All right. And so just like we always do with constraints or Dirichlet type boundary conditions, we substitute those rows entirely with zeros, with the exception of the diagonal term. So the diagonal term, we're going to put a 1. Okay. And then in the forcing vector, we're going to put zeros on those rows as well. Okay. Effectively, we're putting in the equations d1y is equal to 0 and theta 1 is equal to 0 from those first two rows. Okay. All right. And then the other constraint that we're applying here is on node 3. That's going to be on d3y. And so let's go ahead and do the same thing. We're going to go ahead and eliminate that row. We're going to put zeros in the row, except for the diagonal entry. We're going to put a 1. Okay. And then we're going to set f3y equal to 0 as well. All right, good. All right, and then the last two boundary conditions that we're going to apply are going to be our two loads. Okay. So both of our loads in this problem are applied at node 2, right? So we have a downward force P applied at node 2, and we have a counterclockwise moment applied on node 2 as well. Okay. Okay, so the thing you have to be careful about with these forces is the signs, of course. Okay. And so first thing, we have the force that's being applied on node 2. And so that's a force in the downward direction. And so we're going to apply that with a minus P. Okay. In the row for d2y. Right? So we're going to leave the matrix alone, and we're only going to apply the force in the forcing vector. Okay. And again, it's a minus b because the force is applied in the downward direction. Okay. And then we have the force that's being applied on the theta 2 degree of freedom. And so that's going to be an m2, or that's our m, excuse me, just m. And since it's in the counterclockwise direction, we are following basically our right-hand rule. And so right-hand rule basically says that counterclockwise is positive. Okay. And so we have a positive m on that row. All right, and then last thing we have to set is M3. So we don't have any boundary conditions applied on the rotational component of node 3. And so that means we can just set M3 equal to 0. Okay. But we're going to leave the matrix alone on theta 3 just because it's not constrained. Okay. All right, and so with that, we are all set up. And so this is our global linear system. Okay. And so if you actually wanted to solve for the deformations and rotations at the nodes, you'd have to, of course, plug in numbers and solve this event. Okay. Okay. But yeah, you can see with beam elements, nothing really changes about our methodology. We're still using the exact same, direct stiffness formula. We're going to kind of beat it till it's a dead horse and then beat it some more, right? But the only thing that's different here is the element stiffness matrices, which are of course different. Okay. All right. Any questions on this example here? Okay. All right. So that's our first example using beam elements. Okay. Before we move on to the next example, I do want to talk about one other unique thing that we can do. Okay. Which is we can compute reaction forces on our beam elements. Okay. So we're introducing this idea of reaction forces in beams, but you can actually apply the same technique to any direct stiffness problem. Okay. Okay. So first, what are the reaction forces? Bless you. Reaction forces, these are external forces that are applied onto your structure at the locations of the constraints. Okay. And the whole point of the reaction forces is to basically balance out any external forces and make sure that we are in equilibrium. So oftentimes, we don't explicitly compute the reaction forces. We basically just say that the constraints are kind of doing its thing, right? But in reality, all forces have to be balanced out in order for a system to be in equilibrium, right? And so what we don't see is that, whenever you have a constraint, there is an implicit force that's being applied from the constraint onto the structure that's maintaining equilibrium, okay? So in other words, it's like this. So let's say that we have a simple cantilever beam here, right? And so let's say that we apply a load at the end of the beam, okay, right? So if we were to look at a problem like this, we can just automatically say that this structure is in equilibrium because we have that fixed support on the left, right? But in reality, what that fixed support is actually doing is that it's applying what's called a reaction force, okay? And so if we were to isolate this beam from the support, right? So we basically just look at the beam just by itself, right? And we have our force being applied at the end, okay? And so if you have a structure that is in static equilibrium, it is not moving. And so what that always means is that all the forces being applied onto your structure, onto your system, they all have to cancel out. Okay. And so that means that this P must have an equal and opposite reaction force in the structure in order to maintain equilibrium. Okay. Okay. And so that force, right, is applied at the location of the constraint. Okay. Okay. So we can define some Fy that is going to be that reaction force. Okay. And for beams actually too, we also can have a reaction moment or reaction torque. Okay. Okay. Because now that we're looking at beams and we can have these forces that are perpendicular, we have to account for bending as well. Okay. So in order to make sure that the beam does not rotate or do anything kind of weird, there also has to be a reaction torque as well. Okay. And so the rule of thumb, basically the rule of thumb for these is that, if your support or if your constraint is limiting a certain type of degree of freedom, that means there's usually going to be a reaction force developed in that direction. Okay. All right. So why is this useful? So why would you want to compute reaction forces? Well, in reality, if you have some kind of engineering structure, the most common points of failure are often going to be where the constraints are, right? Because usually for when you have the constraints, that's where you usually have some kind of bolt or you have some kind of welded joint, right? You have some kind of rivets there, right? And so those are usually the most common places of failure because that's where most forces tend to concentrate. Okay. And so whenever you do an FEA analysis, a lot of times it's useful to compute these reaction forces just so you can see, where are, what structures or what parts of your model, what bolts or rivets or constraints, which ones of those are going to be most in danger of failing. Okay. Okay. So how do you actually compute this? Well, so reaction forces are what I classify to be a post-processing step. And so this is something you compute after you compute your finite element solution. And so before you can compute reaction forces, you need to compute the nodal deformations first, right? So this is very similar to, if you think back to last week when we talked about, near the end of the week of trusses, right? If you wanted to compute the stress in a truss bar, you first thing you need to do is compute the nodal deformations first. So reaction forces are exactly the same way, okay? Okay, so the way to actually compute the reaction forces is that once you do have the nodal deformations, okay, you're going to multiply. So you're basically going to multiply your vector of nodal deformations. Okay. So it's actually very convenient to do in MATLAB because, in MATLAB, you solve your system, you get a vector of deformations like that. Okay. So to compute reaction forces, you just basically take that vector and you multiply it by your global linear system. Okay. But you have to multiply by the global linear system that you found before you applied boundary conditions. Okay. So that means, if you do want to compute reaction forces, you do have to have a little bit of foresight. And so you can't really do what I've been doing in the lecture where I just, when I apply boundary conditions, I just write over it just because I'm lazy. But if you know that you need to have reaction forces, you want to save that matrix that you had before you applied boundary conditions. You can multiply out. Okay. So for example, in the previous problem, right? In the previous problem, we had, well, I already erased it, but we had this matrix here that we had before we applied the boundary conditions, right? And so to get the reaction forces, you're basically going to take that matrix, okay? Right? So this is 12, 6L minus 12, 6L, 0, 0, 6L, 4L squared, yada, 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 okay? So this is from the last example. I'm not going to write out every single entry just because that's going to take forever, right? But if you notice how I started this matrix, this is before we applied our fixed constraint, okay? So, you should have a symmetric matrix. There's no rows that have been taken out, okay? And you're going to multiply that by your vector of nodal deformation. So d1y, theta 1, d2y, theta 2, d3y, theta 3. So this right here is your vector of nodal deformations that you found from the direct stiffness problem. Okay, and then by doing that, you're going to get a vector, right? So you're going to be basically multiplying a matrix by a vector, and so the solution to that is a vector. Okay. And then what you get from that is a vector, and this vector will tell you all of the reaction forces at those nodes. Okay. All right, so we'll do this on the next example, but I did want to kind of go over it first just so you can kind of see, what we have planned. Okay. All right, any questions on this before we do jump to another example? All right, so we only have about 20 minutes left, and so I don't think I'll be able to finish the next example. So we'll finish it up on Thursday. Okay. Okay, but let's go ahead and start. So this example is a little bit more interesting because we're actually going to see how a beam can actually combine together with a spring element. Okay. So we have an assembly of beam and spring elements here. Okay, so just like in the previous problem, let's say we have two beams connected end to end, just like that. So we have element A, element B, node 1, node 2, node 3. Okay. All right, so our setup so far is identical to the previous one. Okay. Except at the end here. So instead of having a pin support at the end, we're going to say this end here is connected to a spring. Okay. And that spring is going to be perpendicular to that beam. Okay. So this is going to be element C. And then the node that's attached to the ground. So we're going to say that spring is fixed to the ground on the bottom node. And so that bottom node where that spring is fixed, we'll call that node 4. Okay. All right. So unlike the previous problem, let's put some numbers here. So we'll say that the length of both of our beams here are going to be the same. So let's say each has a length of 3 meters. Okay. All right. We have the material properties for the two beams. And so we have the Young's modulus is going to be 210 gigapascal. Okay. Our moment of inertia is 2 times 10 to the minus 4 meters to the fourth. Okay. And so these two properties here are going to apply to both of the beams. Okay. And then for our spring, we need a spring constant for that one. So our spring constant for the beam will be 200 kilonewtons per meter. All right, then we can't forget our force. And so we do have just a single force in this problem. We have a force P, okay? So P is going to be applied downward at node 3, and P is going to have a magnitude of 50 kilonewtons. Okay.
That's 210 gigapascal.
210 gigapascal, yes. Mm-hmm. Okay. So just like we typically do in these problems, let's solve this problem for all the nodal deformations. Okay. That's pretty standard. So we're going to go through our direct stiffness method or finite element method to do that. Okay. But one thing we're also going to do is we're also going to compute the reaction forces at every node in the structure as well. Okay. All right. I think that's it. Okay. Any questions? Any questions on this so far? All right, so let's go ahead and get started. So, first thing to do is we need to compute our nodal deformation. So let's follow our finite element playbook. Okay. So first we have is the element stiffness matrices. Okay. We're going to compute that for both the beam elements as well as the spring. Okay. Now the spring here is interesting because technically we have a 2D spring, right? So we have a spring that's rotated upwards. But what you're going to see here is that that spring actually aligns perfectly with the transverse deformation of the beam. And so we can we can actually just use our 2x2 element stiffness matrix for that as well. Okay. Okay. So let's go ahead and start with elements A and B. Okay. So elements A and B are both beams. They have identical properties. And so the only difference between elements A and B are just their nodes. Okay. All right, so let's go ahead and write this down. It looks like in my notes here, I did not write out the Not write out the values for this. So I did everything in simples. Okay. Okay, so for element A, we have EI over L cubed multiplied by 12, 6L minus 12, 6L, 6L minus 12, 6L. Okay. 4L squared minus 6L, 2L squared minus 6L, 2L squared, 12 minus 6L minus 6L, 4L squared. Okay. And then this, of course, is connected to nodes 1 and 2 for element A. So this is going to be D1y, theta 1, D2y, theta 2. Okay. For element B, right? And don't be afraid to do this too. So, especially on the exam. So the exam, you're going to be very strapped for time. And so if you have a situation where you have two elements where their matrices are the same, right? You can just say, quote, quote, same values as element A. Okay. But the difference for element B here is going to be in the degrees of freedom. So element B we know is connected to nodes 2 and 3. That's going to be D2y, theta 2, D3y, theta 3. Okay. So save yourself a little bit of writing. Okay. Now for the homeworks, I do still recommend that you write out the whole thing just because, on the homework, you're not exactly strapped for time. And so, it's good to kind of write it out, compute everything out, plug the numbers in just to make sure that they make sense. But when you're kind of strapped for time, taking an exam or something like that, then don't be afraid to do something like this. This is perfectly fine. Okay. All right, and then let's go ahead and do element C now. Okay. So element C is our spring. Okay. If you really want to be technical, it's a 2D spring where the angle of rotation here is actually 270 degrees. Okay. So you could, take that angle. You can go back to our formula for the element stiffness matrix for a 2D spring, plug that angle in and get all those numbers. Okay. Or you can kind of look at the problem here and kind of notice something about the direction of that spring. Okay. Right. So we know from before that springs can only expand and contract. So they're limited to deformations along its axis, right? It turns out because the spring here is essentially rotated by 90 degrees, right? The axial deformation of the spring actually aligns perfectly with the transverse deformation of the beams, okay? Okay. Right. So they're basically 90 degrees from each other. Okay. And that works out great because what that tells us is that we already need to use D1y, D2y, and D3y, just from our element stiffness matrices for the beams, right? But what this tells us is that, because the spring is aligned with the transverse deformation of the beams, there's no need to introduce additional degrees of freedom for the x direction. And so we can just use the deformations in the y direction. And so that means that our element stiffness matrix for a spring, we can go back to our good old 2x2 element stiffness matrix for this. And so this is going to be a k minus k minus k, k. Okay. And then we know the spring is connected to nodes 3 and 4, but we're only going to consider deformations in the y direction. So this is going to be d3y, d4y. So there's no need to introduce d3x or d4x, right? Because it's impossible for any element in the structure to deform in that direction. Okay. And so, something like this, it definitely pays to kind of, look at your problem and kind of see what simplifications you can do. Because this does save you quite a bit of writing. So, instead of writing a 4x4 element stiffness matrix where most of the entries are going to be 0, you can just use a 2x2 matrix and kind of do it this way. Okay. So definitely look at your problems, look and see, what types of elements that you have, which directions can they deform in, and then use that to, simplify your problems if you can. Okay. Any questions on this? Yes.
Why is it 270 and not 90?
So it's 270 here because remember we always start from the lower numbered node and we draw our x-axis out that way, and then we rotate counterclockwise from the x-axis in order to get that node or that element into that position. So since the lower numbered node is 3, we have to rotate 270 in order to get down there. Yeah. Mm-hmm. I think for 270, I think you end up with the same values as 90 anyway, but it's good to kind of be consistent with with how you do it. Okay, all right, so let's go ahead and move on to the next step, which is assembly. Okay, so this step mostly is going to be the same as the previous example, and so I'm just going to write in that matrix there. Okay, but you have to be careful because this is the first time. Well, I guess technically we mix trusses and springs, but this is the first time we're mixing a spring together with the beam. And so how you actually put that into the matrix, you have to kind of be a little bit careful about because the constants here are different. Okay. Okay. But since the majority of our elements are beams, I am going to put the beam constant out in front. Okay. So that's EI over L cubed. All right. And then let me go ahead and write in our degrees of freedom here. So this is actually the first time we're going to have an odd number of degrees of freedom here. So we're going to have D1y, theta 1, D2y, theta 2, D3y, theta 3. Okay. We need D4y because that's where the spring is connected to. Okay. Now we don't need theta 4. Because there's no beam that's connected to node 4. So node 4 only has a spring attached. And so there's no reason for us to put theta 4 there. We're going to end up eliminating it from our equation anyway. So, so I'm going to stop the system at D4y. Okay. The D1y, theta 1, D2y, theta 2, D3y, theta 3, D4y. Course is equal to F1y, M1, F2y, M2, F3y, M3, F4y. Okay. All right, so let's go ahead and start assembling. Okay. All right, so let's start with element A. Okay. So element A is connected to nodes 1 and 2. It's a beam. Okay. And so just like the previous example, that's going to be this region right here. Okay. Next, we have element B. Element B is also a beam, but it's connected to nodes 2 and 3. Okay, so that's going to be this region right here. Okay, then we come to element C. So this one you have to be careful because, remember the spring does not support any rotational components, right? So element C here is connected to only 2 degrees of freedom, which is D3y and D4y. Okay. So you want to be careful and don't include the row and column for theta 3. Okay, and so let's go ahead and box those entries in there. So we have D3y. Okay, so it's going to be the D3y column and the D3y row. Okay. Next, we have this entry right here, which is the D3y row and the D4y column. Okay. And then we have that one there. So that's the D3y column, D4y row. And then finally, in the bottom right corner there, that's the D4y entry. Okay. Okay, let's go ahead and just fill in the rest with zeros for all the entries that we don't need. Okay. Okay. Oh, I was like, why is this not symmetric? I need an extra row view there. Okay. That's true for a second. Okay. Missing a zero next to D2y. You're probably right. Let's see. Oh, yes, right here. Thank you. Yeah, the odd number of entries is kind of tripping me out. Yeah. Okay, all right. So let's go ahead and fill this in. I think that will be kind of the last thing we have time for today, but we'll pick this up next time. So we'll start with element A. So this is 12, 6L, minus 12, 6L, 6L, minus 12, 6L. Okay. 4L squared, 6L, 2L squared, 6L, 2L squared. Okay. Right. So in the overlap region, we are going to add those entries together. So I'm just going to go ahead and put the result for that. So that's 24, 0, 0, 8L squared. Okay. All right, next we have the same thing, but for element B. That's a minus 12, 6L, minus 12, 6L. If we have minus 6L, 2L squared. Okay. We are going to have an overlap here, so I'm going to leave a little bit of room for us to add. So we're going to have a 12 here, okay, minus 6L, minus 6L, and then 4L squared. Okay. Okay. All right, so last thing we'll do today is we're going to add in the contributions from our spring, right? So normally, we would just add K here. This would be minus K, and then positive K here, right? But you have to be careful. So, one thing to note for the springs is that, one thing to note for the beams, excuse me, is that we have this kind of constant entry out in front, okay? And so when we add the K's to our matrix here, we have to make sure that we account for that constant out in front there, okay? And so instead of adding just K, we have to add K multiplied by the inverse of our constant out in front. So this is going to be K times L cubed divided by E times I, okay? Minus K L cubed divided by E times I, minus K L cubed divided by E times I, and then positive k L cubed divided by E times pi. Okay. We're basically just ensuring that we're doing the reverse of what we had in front. Question, yes.
Is it bad practice to create our own variable for that EI over L cube?
No, you can definitely do that too. And so I only did it this way just because it's just to be consistent with the last one. But if you want to factor out different things out in front, you can definitely do that too. And also, if you just plug in numbers from the beginning, this is kind of a moot point. You just do everything in terms of the numbers.
Okay.
Yeah. All right. Any final questions before we pause here for today? Okay. All right. So we'll jump right back into this when we come back on Thursday. So we're almost done. We just have to apply the boundary conditions, solve it, and then compute the reaction forces. And then for the rest of Thursday, we'll be going over how to deal with distributed motion. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys on Thursday. Oh, creep. So with creep, it depends on on the equations that are used to govern the creep. So for these equations, we usually just have a very basic like E theory equation. So for creeping deformations, we're talking like very small deformations. Usually for those ones, these equations are pretty appropriate for that. So I would say yes, but there are some certain creep situations where you actually have to factor in other factors of the materials. Yeah. So if you have any like viscoelasticity that's going on, then these equations are not going to count for that. So sometimes that is a factor. But if you're just talking just pure elastic creep, then you can use that for yeah.
Have you ever had a class
for like to account for? So I would say maybe like we have advanced like materials here, the advanced structural mechanics of that. So those classes would probably have that. I say probably because I don't teach those classes, so I'm not sure exactly, but that's where it would be. We did used to have a class on continuum mechanics, where I think that's probably the most appropriate for that. But then we don't have anyone that teaches that at the moment. So it's been a while. It's been 4 years since someone's taught that. So that one actually might be discontinued.
That was with Dr. Sanders.
It was, yeah. Dr. Sanders left. He's not here anymore.
He's at the Citadel, if I'm not mistaken.
Something like that, yeah. I still text him on his birthday. His birthday is very easy to remember because he's a math guy, and so his birthday is Pi Day, March 14th.
Oh,
it's very easy to remember. He perfectly embodies the personality of someone that has a birthday on Pi.
I remember I took his, I think, analytical dynamics course.
Oh yeah.
If I'm not mistaken. Oh, I think continuum mechanics, he did that after, I think it was one of his experimental courses.
Yeah, it was.
And he was always going over Hamiltonian and
very
math-based, and it's like, that is very fitting, actually.
He is a math guy through and through.
I think his dissertation was something with math.
So his degree was, he didn't have a degree in engineering at all. He had a degree in applied math. With physics, which eventually that's what engineering is, and so that's why he got a job here. But his way of thinking, his mindset is different than most engineers.
But, I remember. I had a question. Just with writing. Why was it that for the fixed on a fixed condition for a roller, why is our rotation free?
So a roller is essentially a pin support. So it's the same. So the roller is pinned here, so there's nothing constraining the rotation.
Oh, okay, gotcha.
Yeah. Okay. So the only support that constrains rotation is the fixed support.
Gotcha. Okay, that's okay.
These are FEA matrices.
Thanks, Professor.
Yep.
Have a good one.